Hi everyone! By the end of this video, you should be able to write equations for polynomial and rational functions when given different critical values of graphs. To start with a polynomial function, we want the function with lowest degree and rational coefficients that has these numbers over here as sum of its zeros. So just to kind of unpack that, when it says rational coefficients, it means they have to be real numbers, and lowest degree means we could probably find multiple functions with these zeros, but we want the one that has the lowest degree. So is it like quadratic or is it cubic? We will find out, but we probably don't want the polynomial with the 18th degree with these zeros, okay, lowest degree. So if these are zeros, that means x equals 2 and x also equals 1 plus I. Now if we want to write this as a polynomial, we have to go backwards. So originally we had something like x plus 2 equals 0. We solved it and got x equals 2. We want to go backwards and get this set equal to 0 so we can figure out what the factor is. In order to do that, I'm going to move the 2 over here. So I get x minus 2, then it'll be set equal to 0. So this is the factor that represents that intercept. Same thing here, I'm going to move this over. I get x minus 1 plus I is equal to 0. Okay, so if I start to write that as a function, since I have zeros, I can write that function in factored form. So let's start by giving my function a name. Call it smiley face of x, because it doesn't have to be an f. It can be whatever I want it to be called. And these are my factors, so to write it in factored form, I'm going to multiply x minus 2 times x minus 1 plus I. And you could distribute that one negative sign there if you wanted to. Okay, so in order to get this as a polynomial function, I want to write it in standard form. I would go ahead and distribute out all this, multiply it out. But if I do that, you realize we have a problem because I would have imaginary coefficients, and we want a polynomial function with rational coefficients. That means there's something missing in my function. So we can't have a polynomial with i's in it. So every time you have an imaginary or a complex root, it always comes in a conjugate pair. Conjugate pair. Which means that if 1 plus I is a solution, 1 minus I is also a solution. Which makes sense if you think back to our quadratics discussion with discriminant and quadratic formula. If I had something like, in the quadratic formula, negative 2 plus or minus 3i over 4, I would have two zeros here. One would be 2 plus 3i over 4, and one would be 2 minus 3i over 4. Okay, so they always come in pairs. They're the exact same thing except opposite sign in the middle. And that applies to any polynomial. So in order to complete this polynomial function, I would have to consider the 0 x equals 1 minus I as well. So that would make my intercept x minus 1 minus I. Okay, so let's include that in our function, and then we should be able to get rational coefficients. Because remember, if you multiply two conjugate pairs, or complex conjugate pairs, you're going to get all real numbers, because the i's will cancel, and I squared is negative 1. So our other zero is x minus 1 minus I. Okay, so what kind of function would this be then? How many x's do I have? Well, I'd be multiplying x times 1 more x, so this would actually be a cubic function if we had lowest degree. Okay, now technically I could have another function with this 0 and have a fourth 0 at like 1 minus x minus 5, but we want lowest degree, so I'm not going to introduce any other new zeros. Okay, in order to get this in standard form, I want to multiply all of this out, so I'm going to pause the video and do that. I want you to do this on your own. My advice would be to start by multiplying these two together, get an answer, and then multiply it with this x minus 2. So go ahead and do that, and I will come back with the answer. Okay, if you multiply the two complex zeros, you will get this polynomial here. And notice there are all rational coefficients because when you multiply complex conjugates, the i's cancel out again. And that makes sense because if you try to factor this polynomial, you would not be able to. There's nothing that multiplies to 2 and adds negative 2, which means there will be imaginary solutions. And if you multiply the whole thing together to finally get your polynomial in standard form, you will come up with x cubed minus 4x squared plus 6x minus 4, which I would then went and double checked using two resources. One was Desmos, and I even plugged in both forms just to make sure they're the same thing. So here's the blue graph is my standard form, and my factored form is the same thing. Now, you can double check this by saying, oh good, there's a 0 at 2. We don't have any other intercepts because they're imaginary. You can also check this on Wolfram Alpha. Just type it in, it'll give you the roots. So one is x equals 2, and then here are my two complex roots. Okay, so then you have a polynomial function of lowest degree with rational coefficients and those two zeros. Well, actually three when we use our brains a little bit. Our next question to ponder is this the only polynomial function you can write with the given requirements? Well, we kind of already answered that and said I could have a higher degree polynomial. You know, if I threw in another 0 at 5 and I multiplied that out, it would still have those three zeros and it would be a different polynomial. But there's another way to think about this and another way to answer this question. Remember when we talked about quadratics? Let's say you have a quadratic at -1 and a 0 at +2. Is there only one graph I could draw through these 2 points? I could draw a graph that looks like this. I could technically also draw a graph that looks like this. I could even draw a graph that looks like, I don't know, this. So is there only one polynomial function I can write if I'm given zeros? The answer is no, because we don't know what way it's facing. We don't know, what the a value is. When we talked about quadratics, we talked about that a value. So in order to figure out exactly what the function's going to look like, I would need to give you some more information. Maybe I'd give you the y-intercept, or I'd give you just another point to plug in and help you define that a. So what I was doing here is I was assuming a value was just 1. Now, if I gave you another point, like the y-intercept or just a general point, you would have to kind of use that point to determine the width of the function, okay, which we can see in our Desmos here. Let's say I multiplied this whole thing by, I don't know, 2, pick a number. I would still have that intercept at 0, but the way my function is stretched is a little bit different then. So you can see how that a value would change it. Keep that in mind when you are writing polynomial functions. If I give you more information, think about how you would use it to write a more specific and unique equation. Let's move on to rational functions. So remember, a rational function would look something like this. I've called it ETHS of x, and we've got it in its factored form. So I'm going to go back and review what the important information is, and you should be thinking about how I would write this into an equation. The first thing I want to find is my vertical asymptotes, which a vertical asymptote is an undefined value of x, which comes from when the denominator equals 0. Now, vertical asymptote would be a vertical line, so that means x is always the same, but your y value is changing. So it's always an x equals. So I have two vertical asymptotes. One is at x equals -4, and one is at x equals 5. So they might look something like this. Okay. Now, I would need to find my zeros in my horizontal asymptote as well. So as I'm reviewing this information, I want you to think about if I were going to write a function with the given information, so if this was given, where would I put it in the function? So vertical asymptotes would need to go in the denominator, for example. Horizontal asymptote can come from a few different things. It's either the ratio of the coefficients, or it's the x-axis, or it's the slant asymptote, so you need to analyze the function and see what's going on here. In this case, I have an x in the numerator and an x squared in the denominator. So this is one of those bottom-heavy functions, which means a horizontal asymptote is going to be a y equals equation that is at the x-axis here. So it'd be y equals 0. So again, as I'm writing these functions, I want you to think about, okay, if I were going to write my own rational equation, how would I make the horizontal asymptote be at y equals 0? Well, you'd have to make it a bottom-heavy function where the degree in the denominator is greater. Now what if I want to find a 0? Remember, a 0 is an x-intercept, which means your y value is 0. So I'm really asking the question, when does 0 equal this function? In order for 0 to equal a fraction, the numerator would have to be 0 over something in the denominator that's not 0. So in order to find my zeros, it's enough to just look at where the numerator is 0. In order to make the numerator 0 in this case, I'd have to make x equals -2. Which of course we can write that as a point, is -2, 0. Okay, so if I were writing a function again, ask yourself, what would I need to do? If I was given x equals -2, I would need to put that in factored form in the numerator to make that a 0. Now, the only thing we haven't looked at is this -3 here. In order to talk about that, I want to look at a picture of the graph on Desmos. So here's my graph. You can check that important information. I have a 0 at -2 like I wanted. My vertical asymptotes are at -4 and +5 over here. and my horizontal asymptote is at 0. Now remember, a graph can cross the horizontal asymptote, which it does in this case. What the horizontal asymptote really does here is describes the end behavior. So at the ends of the function, the right and the left end, this function should be approaching 0, which if you keep going, it will get closer and closer to that value. Okay, so now what does this -3 do to the function? So if I have the -3, here's what it looks like. If I have removed the -3, all of a sudden it reflects over the axis. So if I put in a negative, it'll reflect, and if I add the 3 in, it'll change, the wideness or steepness of the function. So what that -3 is really your a value, like we talked about in quadratics and polynomials. Now, if you're writing a function, in order to get that -3, I would need to give you some other information, like another point. So say I give you all this information, and I also say the function crosses at, I don't know, say a point is 2, 5, which I'm totally making that up. That's not accurate information. But if you're given another point, you can throw in an a value, plug in 5 for the y, and 2 for the x, and you could solve for the a value, just like you did with quadratics. If I don't give you another point, you can't find the a value, which is kind of like what I talked about up here. You had the intercepts, but I didn't know how wide it was, so there were multiple polynomials I could have written. So keep in mind, if I'm given this information and I want to go backwards, you need to think about where this information lives in the function and then write it in its factored form. At the end of the day, I could distribute this out to get it in standard form as well. So that was a little bit of a review of things you've already learned. It's a good review for the test, but it's also going to help us think about how to write functions. So please write any questions down and come to class ready to ask them. Have a good night.